Record. Good. So lecture 3 in number theory. So let's review a little bit about what we did last week. In number theory, we studied the integers, z, positive, negative, and 0. And with the integers, you can add and subtract them. And addition and subtraction satisfy some simple properties and very nice properties. And they give an example, one of the most important examples of what is called a group. So in algebra, number theory, and everywhere in mathematics, there is something called a group. And what is the definition of a group? So a group is a set, let's call it G for the moment, with a binary operation which could be written as addition or multiplication. And by binary operation, we mean that for all elements x and y in the group, so we use mathematical notation, this symbol means in the set. For all x, y in the group, there is defined a unique element. I'll write it with a symbol x times y in G. In G. So if x and y were integers and the binary operation were addition, this would be x plus y. If we were looking at, for example, the non-zero real numbers and this operation was multiplication, this would be the product of x and y. So there's a unique element x times y for every x, y, and g, satisfying the following properties. The first is that this operation is associative. So if you take x times y and multiply that by z, I'm using this asterisk to indicate the binary operation. This is the same as x times y times z. So the order in which you do you multiply two things at a time. You can't do x times y times z at once. So this could be x times y, that's an element, and that times z, or y times z, and then x times y times z. But you get the same result, that's associative. Second, there's an identity element. So there exists an element that's called E in G, such that if you multiply any element by E, either multiplying it on the right or multiplying it on the left, you get back the element. So this is the identity. And the third property is the existence of inverses. For all x in G, there exists an element y in G, such that x times y and y times x are both equal to the identity. So a group is a set with a binary operation that satisfies these three properties. And the simplest example is G equal to the integers with the binary operation of addition. So 3 plus 9 plus minus 7 is 12, plus minus 7 is 5, and 3 plus 9 plus minus 7 is 3 plus 9 minus 7 is 2, is also 5. So this is an example of the associative property when written out with the binary operation of addition. And the identity in Z is the number 0. 0 plus 3 and 3 plus 0 is always 3. And the inverse of 3 is the integer minus 3. 3 plus minus 3 and minus 3 plus 3 is always 0. So this is the definition of a group. And some groups, like the integers, also satisfy another property, which is the following. We say that the group G is, there are two words that are used, which are synonyms, commutative or abelian, if the order in which you multiply doesn't matter. X times Y is Y times X for all X and Y in the group. And so, for example, 3 plus 9 is 12, and 9 plus 3 is also 12. So if you add 3 plus 9 or 9 plus 3, you get the same element. That's not always the case in groups. If you multiply 2 by 2 matrices, say matrices with determinant 1, that's an example of a multiplicative group, but it's not commutative. So this is the definition of a group. And so Z is a group. Suppose we look at 2Z. By 2Z, I mean the set of all numbers of the form 2 times n for all n in Z. This is the set of what? 0, 2, 4, 6, minus 2, minus 4, minus 6. This is a set of even integers. And this is also a group. So this set all by itself is a group because there's a binary operation. If you add two even integers, you get an even integer. The negative of an even integer is an even integer. So this set of even integers is also a group. And in fact, if we let D be any integer, at least 1, suppose we let dz be the set of all multiples of D, 0D, 2D, 3D, 4D, and the negatives minus D, minus 2D, minus 3D. This is also a group. It contains 0, and if you add two multiples of D, you get another multiple of D, right? If you have AD plus BD, that's A plus B times D. And if you subtract two multiples of D, AD minus BD, you get A minus B times D. So this set of integers is closed under addition and subtraction. It contains 0. It's also a group. In fact, we have a whole chain of groups. So Z, the integers, contains the even integers. The even integers contain all the multiples of 4, for example. Because any multiple of 4 is a multiple of 2. This contains all the multiples of 20, for example. Because if a number is a multiple of 20, it's a multiple of 4. There are all sorts of subgroups, all sorts of groups contained in the group Z. And we say that the following, that G be a group, the subset H contained in G is called a subgroup of G if all by itself it's a group. So if the identity belongs to H, the subgroup, and if X and Y are in H, then X times Y is in H. And if X is in H, then its inverse, then the inverse of X is in H. So each of these is a subgroup of Z. In fact, 4Z is a subgroup of 2Z, and 20Z is a subgroup of 4Z, and so forth. So we have this concept of a group, and we think of the integers as an archetypical group, and of a subgroup of a group, like the even integers are a subgroup of the integers. The odd integers, what are the odd integers? 1, 3, 5, 7, and they're negatives. Plus or minus 1, plus minus 3, plus minus 5, plus minus 7. This is not a subgroup. Not a subgroup. Because first of all, the identity 0 is not odd. This means not in a set of odd numbers. And the sum of two odd numbers is not an odd number. If you take 7 plus 19, this is odd, but the sum is 26. It's not odd. So the odd integers do not form a subgroup. The even integers do. And one of the basic, so one thing we just observed is that for every positive integer d, the set ZD is a subgroup of Z. In fact, even if we let D equal 0, 0 times Z, the set of all multiples of 0, but no matter what number you multiply by 0, you always get 0. So this is just the set consisting of 0. But 0 is a subgroup. It's also a subgroup because it's closed under addition. 0 plus 0 is 0. 0 minus 0 is 0. And it's a subgroup. This is sort of the trivial subgroup. So that's a trivial subgroup of Z. Okay. Any questions about this? So in mathematics in general, and algebra and number theory in particular, we like to classify things. So we have the notion of a subgroup of the integers, and here we have infinitely many examples of subgroups. For every D, we get a different subgroup, every positive integer D, or every non-negative integer D. And one can ask, are there any other subgroups? Can we find all subgroups of the integers? And the answer to that question is, we already did. So this is a big theorem. It says every subgroup H of the integer Z is of the form H equals D times Z for some unique non-negative integer D. So every subgroup is a set of multiples of a fixed non-negative integer. And another way of saying that is that if you take any set of integers which is closed under addition and subtraction, non-empty set, it has to consist of all multiples of D. And in 300 level math classes, we need to prove things. So this is a theorem, it's an assertion, but it needs a proof. So there's sort of a simple case. If H equals just 0, if H is just the trivial subgroup consisting of only the number 0, then H is just 0 times Z. It's the set of all multiples of 0. So you take D equals 0. And D equals 0 is the only integer such that the multiples of D give you just 0. So if H is 0, the theorem is true, and the number D has to be equal to 0. So suppose this is the trivial case. So the real case is suppose H is not just 0. In that case, there exists an element A in H, which is not 0. Right? I mean, if H is not just the set consisting of 0, it has to contain some non-zero integer. Let's call it A. So if A is positive, we're done for the moment. Suppose A is negative, but we have 0 is in A because A is a 0 is in H because H is a subgroup. Subgroup always contains 0. And a subgroup is closed under addition and subtraction. And so 0 minus A, which is just minus A, is in H. And minus A, if A is negative, suppose H is less than or equal to, not less than or equal to 1, less than or equal to, suppose A is negative, less than or equal to minus 1. If A is less than or equal to minus 1, then minus A is greater than or equal to plus 1. So in every case, this non-zero subgroup H contains some positive element. So H contains positive integers. In other words, the set of positive integers contained in H is not empty. So we can apply what we started with, the very first thing in this course, the minimum principle. Every non-empty set of positive integers contains a positive smallest element. So H contains a smallest positive integer, D. D is positive, greater than or equal to 1. And I claim that, in fact, H is the set of all multiples of this unique smallest positive integer in H. And to prove this, we use the division algorithm. So let A be any element in H. If we divide A by D, we get A is DQ plus R, where this remainder is between 0 and D minus 1. Now, if D is in H, then D plus D is 2D is in H. And continuing inductively, we get every multiple of D is in H. So D times Q is in H, which means that R, which is A minus DQ, so A is in H, D is in H, so DQ is in H. H is closed under addition and subtraction, so A minus DQ is in H, but A minus DQ is R, is in H. And what do we know about R? It's between 0 and D minus 1. Could be any of these numbers. But D is the smallest positive element in H. And if R were positive, it would be strictly smaller than D, which is a contradiction. So R can't be positive. R has to be 0. And if R is 0, A equals dq. So A is a multiple of D. A is in dz. So every element in H is in dz, which means H is contained in dz, which is already contained in H. So H equals dz. So if you take a non-zero subgroup and you let D be the smallest positive integer in that non-zero subgroup, then the subgroup consists of all multiples of D. And D is unique. It is the unique smallest positive element in H. And that is the proof of the big theorem. And really, this is a proof that you have to understand. And almost certainly it will be a question on the first midterm exam, because this is a fundamental result in number theory. Right. Any questions about this before we go on? So let me draw some immediate consequences of this, which indicates some of the reasons why this is so important in number theory. So in studying integers, there is the very basic notion of divisibility. We say that if we have integers, A and B, we say A divides B if A is BQ for some integer Q. So for example, 7 divides 42 because 42 is 7 times 6. Seven divides 91 because 91 is 7 times 13. 7 does not divide, 100. Does not divide 100. Because 100 cannot be written as 7 times Q for any integer Q. We're only looking at integers, right? We're not talking about the fact that 100 over 7 is a fraction. It is a fraction, but it's not an integer. So 7 divides 42, 7 divides 91. 7 does not divide 100. So divisibility is a basic concept, which in fact you learned in elementary school. 3 divides 6. 6 is 3 times 2. That's all we're saying. We say that an integer D is a common divisor of integers A and B if D divides A and D divides B. In fact, maybe I should just introduce it right away, the basic notation. To write D divides A, that's just a vertical line, means this is just the notation for D divides A. And more generally, D is a common divisor of any finite set of integers, A1 up to AK, if D divides all of them. D divides A1, D divides A2, D divides A3, and so on. D divides A sub K. So 7 is a common divisor of of 28, 42, 91, and 770. Because 7 is 4 times 28. 28 is 7 times 4. 42 is 7 times 6. 91 is 7 times 13. 770 is 7 times 110. Right? Another way of writing this is D divides A sub I for all I from 1 up to K. That's the more concise mathematical notation for a common divisor. So for example, 2 is the common divisor of 30, 42, 96. Three is a common divisor also of these numbers, 30, 42, and 96. 6 is a common divisor of these numbers. Right? So this set of 3 numbers has many different common divisors. I could say 1 is also a common divisor. Of 30, 42, and 96. 1 divides every integer. Right? In fact, if I look at this set, 1, 2, 3, and 6, this is the set of all positive common divisors of 30, 42, and 96. And the largest of all these is the number 6. And in fact, 6 is divisible by all the other common divisors. So we use this divisibility property to define the greatest common divisor. The greatest common divisor, or GCD, that's their standard abbreviation for greatest common divisor, is the greatest common divisor of a set of numbers, A1, A2, up to A sub K, is a positive common divisor of these numbers that is in fact divisible by every common divisor of that set of numbers. So the greatest common divisor of 30, 42, and 96 is 6. By the way, common divisors can be negative. I mean, -3 is also a common divisor of these numbers because 30 is divisible by -3. It's -3 times -10. And 42 is -3 times -14. And 96 is -3 times -32. So -3 is also a common divisor. So don't think that common divisors are necessarily positive. They can be negative also. But by definition, the greatest common divisor is always a positive common divisor. Okay. Any questions about this so far? Okay, now we're going to use the theorem about subgroups of the integers to prove a very beautiful representation theorem for greatest common divisors. So this is the following theorem. That A1, A2 up to A sub k be integers, not all zero. Let D be the greatest common divisor of this finite set of integers. Right? If you have a finite set of integers, they're not all zero. The set of common divisors can't be infinite. Because the common divisor is no bigger than the divisor of an integer is no bigger than the integer in absolute value. So there are only finally many divisors. So only finally many common divisors. Let D be the greatest common divisor. So the theorem says there exist integers, not unique. It's called x1, x2 up to x sub k, such that D can be written in the form a1 x1 plus a2 x2 plus a sub k x sub k. So this is what we might call an integral, because the x's are integers. An integral linear combination of a1, a2 up to a sub k. Let me just look at an example. Suppose I take k equal 3 numbers. Suppose a1 is 6, a2 is 10, and a3 is 15. So here I have 3 numbers. The greatest common divisor of these numbers, the GCD of 6, 10, and 15, well, in fact, the largest number that divides all of them is just 1. There's no number bigger than 1 that divides these. Because, for example, what are the divisors of 6? 1, 2, 3, and 6. 6 doesn't divide 10. 3 doesn't divide 10. So the common divisor of 6 and 10 is 2, but 2 doesn't divide 15. So the largest integer that divides all 3 of these numbers is 15. And according to the theorem, we have to write, this is my D, we have to be able to write 1 as 6x1 plus 10x2 plus 15x3. Right? So how can we solve this equation? Well, I guess there are lots of ways to solve this equation. You could take x1 equals x2 equal 1 and x3 equal to minus 1. Because then you will get 6 times 1 plus 10 times 1 plus 15 times minus 1 is 6 plus 10 minus 15 is 1. So here I've written the greatest common divisor of 6, 10, and 15 as this integral linear combination of 6, 10, and 15. Right? That's kind of a simple example of what we're saying. So the theorem says that the greatest common divisor of a finite set of integers can always be written, not necessarily uniquely, in fact, never uniquely, always there are many different ways to do it, but there's always some representation of the greatest common divisor as an integral linear combination of my numbers, A1, A2, up to A sub k. Any questions about what this means? So how do we prove this? So suppose we let H be the following set of integers. All integers of the form A1x1 plus A2x2 up to A sub k, x sub k, where x1, x2, and so forth up to x sub k run through the set of all integers. So all integers of this form. So I claim that H is a subgroup of Z. Well, why is it a subgroup? First of all, if I take the number 0, if I choose all the x's to be 0, I get A1 times 0 plus A2 times 0 up to A sub k times 0. That's 0. So 0 is in this set H. So this set contains 0. And suppose I take two numbers that are in here. Suppose I take, I'll call it U, is A1x1 plus A2x2 up to AK x sub k is in H. And V is, say, A1y1 plus A2y2 plus AKYK is in H. Then, if I add these numbers, U plus V, what do I get? I get A1, x1 plus y1, plus A2, x2 plus y2, plus AK, xk plus yk. If the x's and y's are integers, so are their sums. So this is another integral linear combination of A1 up to AK. So this is an H. So this set is closed under addition, and it's closed under subtraction. I just get x1 minus y1, x2 minus y2, and so forth. So this set of integral linear combinations of A1 up to AK contains 0 and is closed under addition and subtraction. So therefore, it's a subgroup. So by the big theorem, H is equal to dz for some positive integer d. D can't be 0 because the a's aren't all 0, so one of the a's at least is an H, so H is not just the 0 set. So H is some positive integral d, or the set of multiples of some positive integral d. So by the big theorem, every subgroup is of the form dz. And I claim that d is the greatest common divisor. So let's just take a look at this. So H, which is the set of all integral multiples of A1 up to AK, is the set of all multiples of D. So notice that for all I from 1 up to K, the element AI is what? It's A1 times 0, A2 times 0, a lot of zeros, AI times 1, and then everything else multiplied by 0. So if I take the particular integral linear combination of the a's, where the coefficient of A1 is 1 and every other coefficient is 0, that's just the number AI. This is an H. So AI is in dz, which means AI is d times qi. Right? AI is a multiple of d for some qi in z, which means d divides AI for all I. So this number d is a common divisor of A1 up to AK. Moreover, d, which is d times 1, is in dz, which is h, which means d itself is an integral linear combination of A1 up to AK. Suppose we let d prime be any common divisor of A1, A2 up to A sub k. Then every one of these numbers AI is d prime times some integer q sub I prime for some q sub I prime in z. So d, which is A1x1 plus A2x2 plus AKXK, is A1. What is A1? A1 is d prime times q1 prime times x1. A2 is d prime times q2 prime times x2, and so on. D prime, a sub k prime times x sub k. So d can be written like this, but then I can factor a d prime out of this. So d is d prime times q1 prime x1, q2 prime x2, plus q sub k prime x sub k. So d is d prime times an integer, which means d prime divides d. So d is a common divisor of my integers a1 up to ak, and it's divisible by every other common divisor. So this means that d is the GCD of a1, a2 up to a sub k. So d was, we saw, a1q1 plus a2q2. I should just call these x's, doesn't matter what letter I use, plus a sub k, x sub k. So that proves the theorem that the greatest common divisor of a finite set of integers is a linear combination with integral coefficients of the integers. We say that integers a1, a2 up to a sub k are relatively prime if their greatest common divisor is equal to 1. So we saw a few minutes ago that the greatest common divisor of the numbers 6, 10, and 15 is 1. And we get a corollary of the previous theorem that says that a1, a2 up to a sub k are relatively prime if and only if there exist integers x1, x2, x3, and so forth up to x sub k, such that a1 x1 plus a2 x2 plus a sub k x sub k equals 1. And why is this true? Well, if the greatest common divisor of a1 up to ak is 1, then we prove that we can write 1 as an integral linear combination of a1 up to ak. But the converse is immediate, because suppose we have this relation for some integers, x1 up to xk. If D divides a1 and a2 and ak and so forth, it divides every term here, so D divides 1. And the only divisors of 1 are plus 1 and minus 1, and the only positive divisor of 1 is 1. So if this relation holds, then a1 up to ak must be relatively prime. So this is a very useful, very important characterization of the greatest common divisor of a finite set of integers. So for example, if we take a1 equal to 105, a2 equals to 42, a3 equal 30, a4 equal to, let's see, no, a3 equal to 70. And a4 equal to 30. So what is the greatest common divisor of these four numbers? It turns out to be 1. And according to our theorem, there have to be integers such that 105 x1 plus 42 x2 plus 70 x3 plus 30 x4 equals 1. So an interesting exercise is to compute the numbers x1, x2, x3, and x4. That is, solve this equation. Of course, this is just what we've been looking at. It's one equation in 4 variables. It's an inhomogeneous linear equation. But now we're looking for solutions in integers and not in real numbers. Sorry, forget everything I just said. That's correct, but in linear algebra, you study solving an equation, a linear equation of this form, in the reals typically. But here we're looking only for solutions in integers. Yeah. I'll leave that as an exercise for fun. Oops. This is page 9. Okay. Any questions about any of this so far? let's see. How do you actually calculate the greatest common divisor of a set of integers? Well, this is an old problem, and what is by far the most important algorithm, method to solve this problem was actually found in Euclid 2,500 years ago. So Euclid contains a lot more than geometry. There's a lot of algebra and number theory in Euclid. And I want to describe now what is called the Euclidean algorithm. To compute the greatest common divisor, the GCD, of two integers, a and b. And I can take them to be positive. So maybe I'll start with an example so you see the idea. And let me pick an example that's in the text. So this is an example. So the Euclidean algorithm is a process of just successive long division. Suppose I take a equal to the number 574 and b equal to the number 252. And we want to compute the GCD 574 and 252. Right? So this is our notation for the greatest common divisor of these two numbers. So here's what we do. Start with the number 574, divide it by 252. So that goes in 2 times. 2 times 552 is 504, so this leaves a remainder of 70. Now, take 252 and divide it by 70. This is 3 times 70. This is 210, and leaves a remainder of 42. Then I take 70 and I divide it by 42. We get a quotient of 1 and a remainder of 28. Take 42 and divide it by 28. That goes in 1 time and leaves a remainder of 14. Take 28, divide it by 14. That goes in twice and leaves a remainder of 0. Now, if a number d divides 574 and 252, it divides this difference, which is 70. But if d divides 252 and 70, it divides this difference, which is 42. If d divides 70 and 42, it divides the difference, 28. If d divides 42 and 28, it divides 14. And if d divides 28 and 42, well, you get a remainder of 0. So d divides 14. And what does this say? Well, 14 divides 28. So 14 divides 28. So 14 divides 28 and 42. 14 divides 28 and 42, it divides 70. If 14 divides 42 and 70, it divides 252. And if it divides 70 and 252, it divides 74. So every common divisor of 574 and 252 divides 14, and 14 divides both of these numbers. So the GCD of 252 and 574 is equal to 14. So when I do this process of successive long divisions, I get a strictly decreasing sequence of remainders. And the last positive remainder, the last remainder I get that's not zero, is the GCD. So that's what we see in this example. And this algorithm works for all integers. This is what Euclid showed and what I will show right now. So this is an example of using the Euclidean algorithm to calculate the GCD of a pair of numbers. So this is the Euclidean algorithm. Oh, I should also, before I leave this example, where did it go? Yep. 14 is the greatest common divisor. But I can work backwards to actually represent 14 as a linear combination of these two numbers as follows. So let me see if I have enough space, and I'll do it right here. So according to this, 14 is 42 minus 28 times 1. That's 42 minus, but according to this, 28 is 70 minus 42. So this is 42 minus 70 plus 42, so that's another 40. 42 times 2 minus 70. But 42 is 252 minus 70 times 3. So 42 is 252 minus 70 times 3 times 2 minus 70. What is that? This is 252 times 2 minus 70 times 3 times 2. This is minus 70 times 6 minus another 70. So this is minus 70 times 7. But 70 is 574 minus 252 times 2. So this is 252 times 2 minus, what is 70? 70 is 574 minus 252 times 2. That's 70 times 7. So I have 252 times 2 minus times minus is plus 252 times 14. That's 252 times 15 minus 574 times 7. So let me just double check my work. 14 is 42 minus 28. 42 minus, but 28 is 70 minus 42. So this is 42 times 2 minus 70. 42 is 252 minus 70 times 3. So it's that times 2 minus 70. So that's 252 times 2 minus 70 times 6 minus 70 is minus 70 times 7. And 70 is 574 minus 252 times 2. So it's all that times 7. So I have minus 574 times 7. And I have plus 252 times 14 plus 1 is 15. Let's see. I think I made a mistake somewhere, so let me just double check. 42 times 2 minus 70. 252 times 2 minus 70 times 7. Oh, sorry. This is plus 252 times 14, and plus 252 times 2 is 252 times 16. That's correct. So 14 is equal to 252 times 16 plus 574 times minus 7. So here I've written the greatest common divisor of 252 and 574 as this integral linear combination of the two numbers. 14 satisfies this equation. So if you multiply it out, it should work correctly. All right, any questions about this? This is just the example. Now, let's prove the Euclidean algorithm. So I have my integers a and b, and I'm going to do long division. So I want to compute the greatest common divisor of a and b. So let me just start by calling, let R0 be A and R1 be B. So my first step is to take A and divide it by B. I get a quotient Q0 and a remainder. So if I'll call this remainder R2. So just so I'm using, it's just changing notations trivially. So R0 is A, R0 is B, which is R1 times Q0 plus R2. Right? So take A divided by B, this is the quotient, this is the remainder. So divide R0 by R1. Next, divide R1 by R2. Oh, and what do we know about R2? R2 is less than R1 because you're dividing by R1, so your remainder is non-negative, it's strictly less than what you're dividing by. Okay? Divide R1 by R2. So R1 is R2 times the quotient and the remainder R3. And R3 is less than R2, which of course is less than R1. Take R2, so long as the remainder is positive, take R2, divide it by R3, and you get a remainder R4, which is less than R3, which is less than R2, less than R1. And keep dividing the quotient by the remainder. Now, this sequence of remainders is strictly decreasing. R1 bigger than R2, bigger than R3, bigger than R4, but greater than or equal to 0. And I claim at some point, so long as your remainder is positive, you can divide. But you can't divide forever because a strictly decreasing sequence of positive integers eventually has to hit zero. It has to stop. So as we keep going, we'll get let's see. The kth time we do this, r sub k divided by r sub k plus 1, q sub k plus r sub k plus 2. And these remainders are getting smaller and smaller and smaller. And bum, 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 bum. And we get to some point where we have, let's say, Rn minus 2 is Rn minus 1, Qn minus 2 plus Rn. And when you divide Rn by when you divide Rn minus 1 by Rn, we get a remainder of 0. So as you do these successive divisions, your remainders are strictly decreasing. So eventually they hit 0. And the last positive remainder, I claim, Rn, which is the last and the smallest positive remainder, is equal to the greatest common divisor of A and B. So, first of all, if you take any common divisor, let D divide A and B. So D is some common divisor of A and B, which means a common divisor of R0 and R1. So if D divides R0 and R1, divides R2, because it divides this difference. But if it divides R1 and R2, it divides this difference, which is R3, and so forth. Successively, D divides all of these remainders, so D divides Rn. So Rn is divisible by every common divisor. On the other hand, this says that Rn divides Rn minus 1. So if Rn divides itself in Rn minus 1, it divides Rn minus 2. And working your way backwards, Rn divides every pair of numbers, Rk plus 1 up to Rk and Rk plus 2, so it divides Rk. D divides R4 and R3, so it divides R2. It divides R3 and R2, so it divides R1. It divides R2 and R1, so it divides R0. So this last positive remainder is the greatest common divisor, right? That's the Euclidean algorithm. And working backwards from the Euclidean algorithm, you can always express the greatest common divisor as an integer linear combination of your two numbers. Let's look at another example. This is one of the homework problems for next week. Suppose I take A equal 35 and B equal 91. I want to compute the greatest common divisor and write it as a linear combination of these two integers. So I take 91, I divide it by 35. I get a quotient of 2. 35 times 2 is 70, so remainder of 21. Take 35 divided by 21, that goes in one time, and leaves a remainder of 14. Take 21 divided by 14, that goes in one time, and leaves a remainder of 7. Take 14, that's 7 times 2, and a remainder of 0. So the last positive remainder is 7. So the greatest common divisor of 35 and 91 is equal to 7. And in fact, 35 is 7 times 5, and 91 is 7 times 13. So here we see 7 divides 35, 7 divides 91. How do we write 7 as a linear combination of these two numbers? So 7 is 21 minus 14. 21 minus, according to this, 14 is 35 minus 21. So this is 21 times 2 minus 35. According to this, 21 is 91 minus 35 times 2. So I plug that in for 21. It's this times 2 minus 35. So this is 91 times 2 minus 35 times 4 minus 35 times 5. So this says that 7 is 91 times 2 plus 35 times minus 5. So here I've written 7 as a linear combination of these two numbers. Let's just check. 91 times 2 is 182. 35 times 5 is 175. And 182 minus 175 is equal to 7. So it checks. Now there's one more thing we can do with the Euclidean algorithm, which is to write A over B as a very interesting kind of compound fraction called a simple continued fraction. So in this case, sorry, I want to take B over A, take the bigger one. 91 over 35. So according to this, let me do it over here. (91 over 35 is 2 plus 21 over 35. That is, I'm taking this first equation, divide it by 35. I get 91 over 35 is 2 plus 21 over 35. That's 2 plus 1 over 35 over 21. That's 2 plus 1 over, and according to this, 35 over 21 is 1 plus 14 over 21, which is 2 plus 1 over 1 plus 1 over 21 over 14. (21 over 14 is 1 plus 7 over 14, which is 2 plus 1 over 1 plus 1 over 1 plus 7 over 14 is 2. So I have this interesting way of writing my fraction. It's 2 plus 1 over 1 plus 1 over 1 plus 1 over a half. So this is an example of what is called a simple continued fraction. So suppose I have numbers A0, A1, A2, up to A sub n. What this means is this is A0 plus 1 over A1 plus 1 over A2 plus 1 over A3 plus plenty 1 over AN. So for example, if you had, these are positive integers, say 7, 2, 3, 9. This would be the fraction 7 plus 1 over 2 plus 1 over 3 plus 1 over 9. Right? That's what this means. So a continued fraction is something It's a compound fraction where you have like these numerators of 1 sort of built in. Let's just see, what is this number? This is 7 plus 1 over 2 plus 1 over, what is 3 plus a ninth? That's 28 over 9, right? 3 plus 1/9 is 28 over 9. That's 7 over 1 plus 7 plus 1 over 2 plus, now 1 over 28 over 9 is 9 over 28. 2 is the same as 56 over 28. So this is the same as 7 plus 1 over 65 over 28. So this is 7 plus 28 over 65. 65 times 7 is 455. If I add 28 to that, so if my arithmetic is correct, this is 483 over 65. So we would say that this is the continued fraction for the number 483 over 65. And continued fractions turn out to be very interesting in number theory. And in particular, you can get the continued fraction directly from the Euclidean algorithm. So let's go back and see where, here's the Euclidean algorithm. I have this sequence of fractions, and I can just take R0 over R1, R2 over R1. I can work out the continued fraction from this. Let me look at a previous example and just do that one, work that one out as well. I had the Euclidean algorithm for 574 and 252. So let me write that down again. So I have it. My Euclidean algorithm was 574 is 252 times 2 plus 70. 252 is 70 times 3 plus 42. 70 is 42 times 1 plus 28. 42 is 28 plus 14. And 28 is 14 times 2 plus 0. So let me work out from this the continued fraction for 574 over 252. So that's equal to 2 plus 70 over 252. I'm just taking this first equation. If I divide it by 252, this is what I get, which is 2 plus 1 over 252 over 7. Again, they teach you in elementary school that A over B is 1 over B over A. We just use that identity. This is 2 plus 1 over, what is 252 over 70? It's 3 plus 42 over 70. This is 2 plus 1 over 3 plus 1 over 70 over 42. This is 2 plus 1 over 3 plus 1 over 70 over 42 is 1 plus 28 over 42. This is 2 plus 1 over 3 plus 1 over 1 plus 1 over 42 over 28. 42 over 28. So this is what? 574 over 252 is 2 plus 1 over 3 plus 1 over 1 plus 1 over 42 over 28 is 1 plus 14 over 28, which is just a half. This is 2 plus 1 over 3 plus 1 over 1 plus 1 over 1 plus 1 over 2. So this is the continued fraction, which if I write it in these brackets, the partial quotients of these numbers are 2, 3, 1, 1, 2. So that's the continued fraction for 574 over 252. And you'll notice that these numbers 2, 3, 1, 1, 2 are exactly the quotients that I got when I used the Euclidean algorithm 2, 3, 1, 1, 2. So from the Euclidean algorithm, we can do many things. We can find the greatest common divisor of two numbers, a and b. We can write that common divisor, that greatest common divisor, as an integral linear combination of a and b. And I can write a and b as a simple continued fraction. So these are important results in arithmetic and number theory. And you'll have a number of homework problems using them. Okay, well, that's everything I wanted to do today. Are there any questions about any of this? Again, I remind you, the first homework is due midnight tonight.
Professor.
Yes. Go ahead.
Can we ask a question about homework 1?
Yeah, of course.
I had a question about question 17.
Okay. Let me take a look. That's on page one, section 1. Let me find it. That was the proof by induction.
Yes.
So we want to prove that we take the sum of the cubes of the first n integers. That's exactly the same as taking the sum of the first n integers and squaring it. Okay. And we want to prove by induction. So, of course, if you look at the case n equal 1, you just get 1 cubed is 1 squared. So that's true. And if you want more sort of psychological reassurance, if you look at the case n equal 2, 1 cubed plus 2 cubed is 1 plus 8 is 9. And 1 plus 2 squared is 3 squared is 9. So that checks. And if you were to look at the case n equal 3, 1 cubed plus 2 cubed plus 3 cubed is 1 plus 8 plus 27, which is 36. And 1 plus 2 plus 3 squared is 6 squared is 36. So at least for the first 3 cases, we know this is true. But a useful fact in proving this result is the already proved fact that you take the sum of the first n integers, this is n times n plus 1 over 2. So we already proved that. So another way of saying what we want to prove is that 1 cubed plus 2 cubed up to n cubed is n times n plus 1 over 2 all squared, right? So this is the equivalent statement, right? Okay, so I'm going to use this fact. So let me just give myself a clean piece of paper. So assume by induction that 1 cubed plus 2 cubed up to n cubed is equal to n times n plus 1 over 2 all squared. Okay, so this is the starting point. And now consider when we have,
Wait, I have a question real quick.
yeah, go ahead.
So how was you able to get n times n plus 1 over 2 squared?
Well, so this is what we have to prove, right?
Yeah.
But this 1 plus 2 plus 3 up to n, this is the same as n times n plus 1 over 2. So we're squaring that, right? Because if you take the sum of the first n integers, that's n times n plus 1 over 2. But we already proved that, right? That's the previous problem, one of the things, but this we already proved, right? And in fact, you should have already seen that in calculus when doing integrals. The sum of the first n integers is n times n plus 1 over 2. But we proved that using induction already. Right? So when you're proving something, you're allowed to use things that were previously proven. So this is just an equivalent statement of the problem.
Okay.
So now I want to consider the sum of the first n plus 1 cubes, right? I know this is true. I want to look at this. But what is this? The sum of the first n cubed is n. Let me write this as n squared, n plus 1 squared over 4. That's what this is equal to, right? This is n squared, n plus 1 squared over 4 when you square it, plus n plus 1 cubed, right? The sum of the first n plus 1 cubes is the sum of the first n cubes plus the n plus first. And the sum of the first n cubes is this, plus n plus 1 cubed. Now, let me factor out n plus 1 squared from this. This is n plus 1 squared times n squared over 4 plus n plus 1. And this is n plus 1 squared. Let me put this over a common denominator. N squared plus 4n plus 4 over 4. And this is n plus 1 squared. And n squared plus 4n plus 4 is n plus 2 squared over 4. So I'm just doing a little bit of high school algebra here. And what is this? This is n plus 1 times n plus 2 over 2 all squared. But this you should recognize now as the sum of the first n plus 1 integers squared. And that's the end of the proof. The sum of the first n plus 1 cubes is this. Right? So this requires a little bit of algebraic skill, but that's what you have to develop in higher level math classes.
Professor,
Yeah,
I had a question on question 12. Let me just help on that one.
question 12. Okay, let me take a look.
Yeah.
Okay. So homework 12 was prove that if D divides A and D divides B, right? This vertical line means divide. Then D divides the integer AX plus BY for all integers X and Y and Z. So one proof can go as follows. D divides A means I can write A as D times, say, Q1 for some integer Q1. And if D divides B, then B is D times Q2. This is for some Q1, Q2 integers, right? That's what divisibility means. So consider, take any X and Y, consider AX plus BY. But A is D times Q1, so this is DQ1 times X. And B is DQ2, so this is DQ2 times Y. And from this, I can factor out a D, because I have a D here and a D here. This is D times Q1X plus Q2Y. So AX plus B is D times some integer. So D divides AX plus BY. And that's the end of the proof. That's what we needed to prove.
You can choose any letters, or you have to like choose Q.
No, whatever your favorite letters are, you know, make this R, make this S, doesn't matter. This would be R, this would be S. Doesn't matter,
Okay, I see.
right? You know, it's like if your variable is X or Y or Z or UVW, it's up to you. It doesn't matter.
Can I see 17 again, please, on the last part? Mm.
Right? Any other question?
No, thank you.
Okay, all right. I'll post this video very soon on YouTube. Okay, so be well. Bye-bye.